Here we come.
So safety is one of the biggest concerns of consumers, because if it's not safe, nobody's going to willing to buy the car. On the diagram here, we can see a car that was damaged by fire last year in 2008. And the car was a converted Prius hybrid that consisted of lithium-ion batteries. And apparently the lithium-ion batteries and some connections which failed and induced some spark, and the battery actually catch fire. And fortunately, the driver was okay because he smelled the smoke earlier, so he jumped out and he drove the car on the side of the highway, but the car was totally damaged. So you can see that this is one of the things that we have to make sure when we build cars with lithium-ion batteries, they have to be safe. And how to make them safe? That's very difficult, because safety and failures, and they are just two different things. But failures of a battery, also lithium-ion battery, can come from different reasons. It can come from unbalanced charge, overcharge, over-discharge, overcurrent, and overheating. And the batteries can get electrolyte spill, as shown on the diagram, where when the failure happens, there is electrolyte spill of one of the cells. But once this happens, the whole battery module is bad. Therefore, you cannot continue to use it. In addition to the battery failure itself, you may also find that electronics attached to the batteries can also fail. And then those failures can cause further failure in the system. Therefore, the design of such system can be very challenging in terms of safety. Talking about the safety, for lithium-ion batteries, there is a safe range that we need to maintain no matter what happens when we use the battery. In addition to those that we mentioned, such as overcharge, over-discharge, overheating, and so on. Maintaining voltage of each battery cell within a certain voltage range is also very critical. So you can see here, if you discharge the battery too much on the iron phosphate battery, if you drain the battery to below 2.7 volts, and that's going to create some premature damage to the battery. So therefore, in real life, you want to prevent that to happen. You want to maintain the battery voltage roughly about 2.8 volts. On the other hand, if you charge the battery voltage to too high, you can also have some premature failure happen, premature damage to the battery electrodes. Therefore, you want to maintain the battery roughly no more than 3.8 volts on iron phosphate batteries. On some other chemistries, the battery range, voltage range may be different. But overall, there is a range when you charge and discharge the battery. You don't want to overcharge, you don't want to over-discharge. And in addition to that, you want to maintain the current within a given allowable range. You want to maintain temperature in the range, therefore you can have a safe system. To overcome the issues related to lithium-ion batteries, a lot of battery manufacturers have been working hard to improve the chemistry and the control and the management of those batteries. With the U.S. government stimulus package coming up this fall, the proposal already in the process of review. With all this Recovery Act, the $2 billion for battery manufacturing development, and it's going to help help improve the lithium-ion battery safety. The cell and the battery pack manufacturing facilities, battery material supplies, recycling facilities, they're all included in the battery manufacturing stimulus package. The stimulus package, in addition to that, also support PHEV demonstration projects. And this, again, with a demonstration with a much bigger fleet in operation, it will demonstrate and discover a lot of things that may not be discovered within just a small number of vehicles deployed. Within all this demonstration project, a minimum of 150 PHEVs will be demonstrated in each project, with total 8 projects anticipated, you're going to see a lot of fleets that are under evaluation. And again, this is going to improve the safety issues. The government is going to provide tax to battery manufacturers, plug-ins, and so on. For example, for plug-in HEV, they're going to provide tax incentives to the buyer, anywhere from $2,500 to $7,500 for a battery-powered PHEV with energy storage minimum 4 kilowatt-hour to maximum 16 kilowatt-hour. And also, some of the states, like Colorado, will pay the difference between HEV and a PHEV for the consumer. So all this stimulus are going to push PHEV in a new stage in the next couple of years. So that's related to batteries. The next topic I want to discuss a little bit about ultracapacitors. Ultracapacitors, even though they are not considered as a viable solution yet, but they do offer some unique advantage because these ultracaps have very high power density. In the earlier section, we discussed lithium-ion batteries. We talk about high energy density and high power density and so on. However, when you have a high power density lithium-ion battery, their energy density are usually sacrificed. So therefore, if you want a high power cell, you will have a lower energy available. And if you have a high energy cell, you're going to have less power available. You cannot satisfy both at the same time. To benefit for the driver, the more distance is better. Therefore, you want a high energy cell. But on the other hand, you don't want to sacrifice the driving performance. So you're going to need high power. So that dilemma may be offset by using a portion of the energy storage system with Ultracap. So Ultracap is an electrochemical energy storage system, very similar to battery, but it's also different from battery. It got a very high energy density and specific energy. But the problem is the energy density is low. The power density is high, but energy density is low. So therefore, for the same amount of energy, you need much larger size. At the current time, the energy density of Ultracap is roughly 1/10 of lithium-ion batteries. But the power density is roughly 10 to 50 times lithium-ion batteries. So that's where the chart shows the diagram of Ultracap. Well, you can see that the collectors also similar to the electrodes in the Ultracap. In the battery, the collector of Ultracap is similar as the electrode in the battery. They're on the outside. And inside, there's electrolyte, and then the dielectric between the two collectors. The energy stored in the Ultracap is 1/2 CV squared. C is capacitance, V is the voltage. So in order to increase energy, you have to increase the capacitance or you have to increase the voltage. To increase the capacitance, you need to increase the size, increase the area, or reduce the distance. Reducing the distance is based on the strength of the dielectric or the breakdown voltage of a dielectric. And so increase the size is the only way to get more capacitance. Increased voltage is also limited by the breakdown voltage of a dielectric and a capacitor. Therefore, you do have some limitations. The Ultracap is a very simple device. It's very similar to an ideal capacitor with a resistance in series. There is a small leakage in current. Therefore, there will be a parallel resistance with Ultracap. So the diagram, the equivalent circuit is very simple, much simpler than the battery, because in a battery, the internal resistance is not constant, but in Ultracap, it's relatively constant. The discharge of Ultracap, as an example, 2600 farads, 2.5 volt cell Ultracap, you can see that the discharge current can go from 50, 100, 200, 300, 400 to 600 amps. So it can be discharged at a very high rate. And that is something the lithium-ion battery can never achieve. Useful energy on Ultracap is also very large. You can discharge Ultracap almost down to zero. But of course, if the voltage is too low, you may not be able to use it. But ideally, it does not damage the life of Ultracap if you discharge the voltage down to 0 volts. And since it's not damaging the life of Ultracap by discharging the Ultracap, you can basically run millions of cycles on those Ultracaps without problem. So the lifetime of Ultracap is definitely not an issue when you use them. The only issue at this moment is energy density, the large size. To calculate the SOC of Ultracap is very simple because it is proportional to voltage squared. 1/2 CV squared is the total energy. So you take 1/2 CV squared divided by another 1/2 CV squared, you get the SOC. Well, the denominator is a full rated voltage. The denominator is the actual voltage. Specifications of Ultracaps made by Maxwell Technologies with 4 different units listed here. One for a battery, one for Ultracap cell, one for Ultracap module, and one for another Ultracap module. The capacitance is 2600 farads on the cell. When you put some in parallel, when you put some in series, actually the capacitance is going to decrease. When you put them in parallel, the capacitance is going to increase. And you can see that the internal impedance of Ultracap is only 0.7 milliohms. It's very small. Even for the module, it's only 10 milliohms. The voltage, each of them is 2.5 volts on the cell, 42 volts on the module, or 14 volts on the second module. And there's some other parameters for the Ultracaps, and you can read this later on. As we mentioned that ultracapacitors have very high power density but very low energy density. In order to take advantage of the power density of Ultracap and high energy density of lithium-ion battery, we can put them together to form a hybrid energy storage system. Looking at the chart here, we have a hybrid energy storage system where there's a high energy device, there's a high power device, and then we will have power converter to control power flow between the energy storage system and the load. So when you have, in this hybrid energy storage system, when you have high power demand, the power comes from the high power device in addition to the high energy device. When you have low power demand, the high energy device would put some energy to the high power device so that it will be ready to be used. On the other hand, if the load is in regenerative braking mode, you can put all the energy in the Ultracap within very short time duration, and afterwards you can take the energy out to put it in a low energy storage, low energy density device. So in system like this, you can increase your energy capture capability during regenerative braking a lot, and so therefore you can increase your system efficiency. And you can also reduce the size of the energy device because you have the Ultracap to provide power. A typical arrangement like this would require, if you look at the next diagram, would require a certain amount of Ultracap and a certain amount of high energy battery. So the high energy battery, for example, in a PHEV, if you have, let's look at this right down here. If we have a PHEV and we calculated that we need 11 kilowatt hour of energy for the PHEV for 20 miles distance. If we use lithium-ion battery only, let's say you're going to need 400 pounds. Okay, that may not be including the packaging material and so on. Because this 11 kilowatt hour, suppose we can discharge at 4C. C is the rate. C is called C rate, is the battery discharge rate at rated energy. So in this case, C is equal to 11 kilowatt. Okay, so if we discharge 4C means we can discharge at 44 kilowatts. So this is really enough for a SUV type PHEV. So the volume is 400 pounds. So in order to satisfy power of 70 kilowatts, you need 6C of actually rather 7C. Therefore, the weight, if you have to select a different battery, not the one that we just talked. So you have to select a weight roughly 500 pounds. Or you have to reduce energy from 11 maybe to 9. So that's the lithium-ion battery. If we have an Ultracap in the system, let's say we're going to have a 10 kilowatts lithium-ion battery, which is going to be roughly 360 pounds. That's a good battery. And then we have 1 kilowatt hour Ultracap. And that may be weighted at 40 pounds. And this one is going to give you a roughly 44 kilowatts. Most of the lithium-ion batteries are capable of 4C. And this one can give you roughly more than actually 100 kilowatt rate. So altogether, you can get 144 kilowatt rate. So it's sufficient to drive a REEV. Remember the setting wheel, the Chevy Volt. The Chevy Volt has a motor that is 125 kilowatts. And they have a battery at 16 kilowatt hour. So you can see the rate at maximum power is roughly 8C in the system. So that battery is considered a high power battery. But when we use a high energy density, we can significantly reduce the weight of the battery pack. Or if you use the same size and same weight, you can increase the total energy available, thereby more distance for the vehicle to be driven. Get back to the diagram on the screen. In order to take advantage of the energy and power on the two systems, you usually are going to need a power management device, typically a DC-DC converter, bidirectional, so that can manage the Ultracap and the battery. So the idea is, in normal driving, you want to slowly charge the Ultracap from battery so that the Ultracap will have a sufficient energy available for acceleration. Now, when the vehicle speed is high, you want to discharge the capacitor a little bit so that it will have enough space left for regenerative braking. So the Ultracap SOC will highly depend on vehicle speed. If vehicle speed is high, you want to leave room for regenerative braking. If vehicle speed is low, you want to charge the Ultracap so that you will have energy for the next round of acceleration. So therefore, the Ultracap is controlled by the DC-DC converter in these systems. So now we're going to move on to the next topic about battery management system. We discussed about battery. We look at the issues related to lithium-ion batteries, including the safety, capacity fade, and the life cycles. And also we discussed how to put the two energy systems together, including Ultracap and a lithium-ion battery. In order to manage those batteries, in order to provide a safe, reliable operation, and in order to extend the life of battery, a battery management system is critical. And that's a piece of device, that piece of system that is definitely needed in any PHEV, EV, and HEV. The battery management system, also BMS, we're going to look at the basic requirement, the structure, and the importance of cell balancing, how to extend life and capacity of a battery using BMS, voltage, temperature, health monitoring, current sensing, SOC calculation, temperature compensation, and so on. So we're going to look at a few issues on this battery management system. The basic requirement of a BMS include the voltage, current, and the temperature monitoring. Also state of charge, which evaluates how much energy left in the battery. So those four things are the basic requirement of a very basic BMS. A better BMS would provide protection other than just monitoring. The protection will avoid overcharge and over-discharge of the battery. An even better BMS would provide cell balancing. And I will discuss what is cell balancing in the next few slides. And thermal management to take charge of cooling and heating of the battery. And why cooling? Because when battery gets hotter, it will provide less energy available. And in some cases, you may have to stop using the batteries. In extremely cold weathers, the battery energy will drop very significantly. In that case, it's better to heat up the battery so that you can have energy available from the battery to drive the vehicle. So lastly, safety, life extensions, and capacities, those things are incorporated in advanced BMS system. Monitoring of battery voltage, current, and the temperature SOC, those are relatively easy once you have a system in place. But balancing of those batteries are not so simple. So I want to start looking at a 4-cell in series, a system that has 4 cells in series, and what happens when the cells are not balanced. On the diagram that you see here is a system that consists of 4 battery cells, but those 4 cells are fairly balanced. They are very good, consistent battery cells. Each of them are 3.65 volts when they are fully charged. So when we have such good batteries in place, we can simply monitor the terminal voltage of that string. If we know the string voltage reaches 14.6 volts, they are fully charged. We can stop charging, and then we can use the batteries. And then we can charge the next time. We just continue to measure the terminal voltage. But what happens is, within all these batteries, there's no way you can make them 100% consistent, no matter how well you do in the chemistry. Even you may have a fairly consistent battery cells in place, but due to the arrangement of batteries in a real-life system, they may experience different voltages. They may experience different cooling. Therefore, the chemistry over time could deteriorate at a different rate. So over time, they will become inconsistent. When they become inconsistent, what it means that the voltage will start to be different from each other. So the next diagram you will be seeing is the same 4 battery string. But over time, we didn't do anything with the battery. So every time we only measure the terminal voltage. After maybe 2 years, you can see that one of the batteries is already 4.8 volts, but another battery cell only 3 volts. And this creates a huge issue for you because the 4.28 volt cell could be potentially dangerous because it is way overcharged. The 3.0-volt cell is undercharged, so therefore it will not have enough energy for you to use. So in a system like this, you may think you fully charge the battery, but due to that low voltage cell, there's no energy available for you. At the meantime, the 4.8 volts battery cell could potentially be very dangerous. So therefore, without balancing, a battery system could deteriorate to the point that it is no longer useful. And it happens to consumer electronics because normally we don't monitor the battery voltage on the cell level. A second example shows a 60 battery module in a system that has 15 modules. Each module has 4 cells, so therefore you see 4 voltages, V1, V2, V3, V4 in each module. What you can see here is this system, without balancing, without BMS, over a few months, the battery voltage has changed. The lowest is 3.28 volts, the highest is 3.69 volts. This is also a huge difference, which is the reason why the vehicle can be driven for 25 miles at the beginning, but only about 15 miles after 6 months, because the voltage has changed significantly. So therefore, it is important to do the balancing. The balancing is not a new concept. It actually started in the 1950s and 60s. People started to use resistive balancing, and then later on capacitive and inductive balancing. And those methods have been working very well, and we'll look at how they work. In a resistive balancing, each battery is shorted by a switch with 2 resistors. In the control of this system, we try to identify the batteries that has a high voltage. When we find a battery cell that has a high voltage, we will close the switch so the energy of that cell is consumed on the resistance. And then we start to do that for every cell until all the voltages are very similar. Once they are very similar, the balancing process is finished. The system like this would provide a lot of benefits. A study was done on lead-acid battery about 20 years ago. The diagram that I took from that study is shown on this chart. The pink curve shows a battery system with balancing. The blue curve shows a battery system that did not have balancing. Over 160 cycle test, after the 160 cycles, you can see the capacity, the available capacity on the 2 systems are very different. They are roughly 25% different over 160 cycles. What does it tell you? That the battery cells with the balancing system are going to be providing much more capacity available, and it's going to last much longer than the batteries that did not have a balancing system. However, a system like this will not be very efficient because you're wasting energy on the batteries, on the resistors. So those energies are wasted. We have to deal with the heat, and we have to deal with the size of those resistors, so the system may not be very practical. So later on, people developed a capacitive balancing circuits by putting capacitors in parallel with batteries and with switches. So when the switches on the diagram over here, we have 4 batteries in series, and we also have 3 capacitors in parallel with the batteries. When we switch on the top, the capacitors get charged by the battery B1, B2, and B3. And the next moment, we're going to switch them on to the bottom. Therefore, the batteries are going to be in parallel with the capacitors. It's B2, B3, and B4. At that time, if any capacitor has a high voltage, it's going to be discharged to the batteries as a lower voltage. Now, when you switch them on top, any capacitor that has a high voltage will be discharged to the battery. Any capacitors that have a lower voltage will be charged by the battery. So this is very energy efficient. However, due to the size limitations of the capacitors, it may take a very long time to balance the batteries. Some studies showing that it takes up to 20 hours for a system that are very unbalanced. People also developed multi-winding transformer balancing, which is called inductive balancing for a battery system. In this system, the primary of the transformer has one winding, which is connected to the battery string. The secondary have many windings, which each winding connects to each cell of the battery system. In controlling the system, we will switch on the primary side of the transformer so that the current will build up on the primary winding. Once the current is built up, we will open the primary winding switch, and at the meantime, we're going to identify which cell is having a lower voltage. In a system like this, we have number 5 has a high voltage, but number 2 has the lowest voltage. So we're going to close the switch connected to battery cell number 2. So the energy on the primary winding is going to be transferred to the secondary winding, and that is going to be charging battery cell number 2. So we start to do this for every cell. We identify the lowest cell every moment until all the cells have very similar voltage. At that time, the balancing is finished. The problem is building such a multi-winding transformer is very difficult, and the size could be also a concern in such a system. So in the past 2 years, at our laboratory, we have developed some systems which can do a better charging, a balancing as well. So we're going to look at a few things that how we can potentially solve some of the issues related to those systems we just discussed. The first thing is this is charging. When you charge the battery, there are a number of different topologies that you can use to design the charger. One of them being an isolated bidirectional charger. Well, you can realize the V2G function. So in this system, we have a bidirectional charger. So you can see that there are 3 edge bridges. The first edge bridge on the left is the one that converts AC to DC. It can also convert DC to AC when you transfer energy from battery to the grid. And C1 forms a DC link between the grid and between the right hand. On the right hand of C1, it's an edge bridge that converts DC to a very high frequency AC to connect to the primary winding of the isolation transformer. The transformer is a high frequency transformer that transfers the high frequency AC on the primary to the secondary. So on the secondary of the transformer, you have another bridge that acts as a rectifier during charging of the battery. During discharge of battery, that acts as an inverter to convert battery voltage into a high frequency AC. So the isolation is done through the isolation transformer. Because it's a high frequency isolation transformer, so the size is quite small. At the meantime, because the isolation transformer can be designed so that we actually can do inductive charging, so which means there's no electrical contact between grid and the battery. All you have is an isolation transformer that is designed as an inductive charger. A second thing that we have developed is a balancing IC that can balance the batteries during charge. The diagram over here showing again 4 battery cells in series. Each one of them has an IC in parallel with the battery. The IC is a smart device that can automatically turn on when the battery voltage reaches a certain level. In this particular design, we use iron phosphate batteries, so the IC is designed at 3.65 volts. So during charging of the battery, the IC will continuously monitor the voltage on the battery cell. Once it sees the battery cell voltage reaches 3.65 volts, it's going to start bypass current. At the meantime, it's going to send a signal back to the charger saying, well, the cell is already full, so you need to reduce the charging current, but still keep charging the rest of the batteries. Once the second battery cell is full, you do the same thing. The third, until all the battery cells reach 3.65 volts, you're going to stop charging. So that process, during that process, all of the batteries are charged full. rather than the one that we saw earlier. You will say one cell 3 volts, other cell 4.8 volts. That's not going to happen. Those ICs, as I said, are smart ICs. They can be designed to have a wake-up pin. When a charger is in place, the ICs are going to start monitoring the battery voltage. When the charger is not present, the ICs are disabled so that they don't consume energy from the batteries, even though they are in parallel with the battery. But when charge is present, they're going to wake up to start monitor the battery voltage. When the battery voltage reaches preset limit, they are going to start bypass current. So you probably already see an issue, is that when they start to bypass current, they're going to waste energy because their voltage is equal to the battery voltage, and the current flowing through these ICs are going to waste energy. Well, the good thing that in a hybrid electric vehicle, we're going to do the balance every time we charge the battery. Because you do it every time, the imbalance between battery cells are very small. Therefore, you're not going to need a lot of energy to balance the cells. Our experience is that with a 7 kilowatt hour pack, we need roughly 25 to 40 watt hour every day to balance the cells. With the 11 kilowatt hour pack, we need roughly 50 watt hour to balance the cells on a daily basis. And we said that we reduce the charging current when one of the cell reaches full. So those ICs are very effective in terms of doing the balancing. Because the ICs that they're designed with a very small size, each of them can conduct 700 milliamps of current. So this is very good for smaller battery cells. If you get large format prismatic cells, if you want to balance them at a higher current, you can put them in parallel to increase the balancing current capacity. The accuracy is very high. You can go all the way up to 2 millivolts accuracy, but in real life, 5 to 10 millivolts is very practical. And as I mentioned, there are enamel pins. Well, you're going to enable the ICs when a charge is present, but in the future design, apparently a wireless communication can be designed with those ICs that can communicate with the charger without a lot of wiring. That charge balance is going to solve the imbalance issues during charge, so you can make sure that every battery is full. But still, due to the chemistry difference, due to the arrangement of batteries, different temperatures, and so on, so some batteries, even though they have same voltage, but they may have lower energy, in fact. So in that case, the best way is to do a dynamic balance. A dynamic balance of battery is similar to the capacitive balancing and the inductive balancing mentioned earlier. Is a very complex system to be designed, including the switches, the switch control, the switch arrangement, and the size, and so on. In order to reduce the overall size and simplify the control, and we have developed a bidirectional DC-DC converter-based dynamic balance. So in this balance system, we have a number of switches, but we only have one DC-DC converter instead of many capacitors in the system, or a multi-winding transformer. This DC-DC converter is trying to get energy from the string and then try to charge the lowest cells in the string. Once all the cells are charged with similar voltage, it's going to stop. Every time it identifies a lower cell, it's going to charge that cell from the string. So it's very effective. Because we have only one DC-DC converter in a large string, the size of the system can be relatively small for this balancing system. The next topic, I'm going to talk about battery charging. So with battery charging, how do you charge the battery? What is the requirement? And what is a fast charging? What is slow charging? And why do you do bidirectional charging and so on? So let's look at a few of these concepts. The charging requirement is defined by SAE a number of years ago when they developed electric vehicles in the 1990s. There are a few standards available already in the SAE system, including conductive charge, inductive charger, and a conductive charger. GS1772 for conductive charger and GS1773 for inductive charger. There are a number of other standards related to this, and you can look up these standards and find out what part is applicable to a charger design and to actually a vehicle system design. In GS1772 and GS1773, they divided the charges into 3 different levels. In level 1, level 2, and level 3. Level 1 charging, which is just a normal charging socket plug, for example, at your home. If you have a 15 volts, 15 amps, 110 volts socket, you can use that to charge your battery. So that's small charging current, level 1. In level 2 charging, it may not be a dedicated outlet, but it got to come with cable protection, or you can have a dedicated socket for the charging. And it also covers DC power and a bidirectional power flow. That's level 2, up to 200 volts, 240 volts AC, up to 80 amps in a dedicated 5-pin plug. Okay. So level 3 charging, more looking at commercial vehicles where you can have a really high current, 600 volts, 600 amps of charging current. The GS1772 defined a level 2 charge as a 5-pin connector, and we are showing here. The 5-pin with 2 of the pins are positive, negative, 1 of the pins is ground, and 2 communication pins. The reason that you need a communication pin is something that we mentioned earlier. We want to charge the vehicles at the late evening time. You don't want a consumer to wake up in the middle of the night and plug in the vehicle to charge. So the way to do this is that you have a smart device built in with your vehicle charging system. And that smart device can do a few different things. For example, you can set a timer so you don't start charge until a certain time in the evening. Secondly, you can have that smart device to communicate with the utility company to ask for information, whether it's a good time to charge my car. And if the demand is high on the line, it can tell you, yes, you can charge, but the price is going to be high. Or they will tell you that, yes, you can charge, and the price right now is low. So the ping pong between the charger and the utility communication center is critical to determine when and how to charge the battery. For example, it can tell you that you can charge, but please charge at lower rate because the power demand is high at this moment. So the diagram here shows the connection between a car and the charger plug. The charger plug. You can see that there's a charging that can go either 110 or 240 volts. In charging, people are talking about 2 different charging devices. One is conductive, one is inductive. The conductive would have a power plug where you can plug it into a socket. So that's conductive. Now in conductive, you can conduct high current, no problem. But the problem is that many people worried about what happens if you have a small child, if it's a woman that is scared to plug in that large power device. So in that case, you can go to inductive charging. In inductive charging, there's no direct current contact, no direct conductor contact. Basically, you have is a mechanical thing that you can plug in from one to other to realize the charging. Because there's no current contact, so it's relatively safe to operate. But because inductive design, that you can not realize high current charging, so it's usually a level 1 charger with a small charging current. The inductive charger is usually realized with isolation transformer, and that transformer has 2 windings, one on the primary and one on the secondary, and those 2 are separate. When you put them together, it will induce voltage from primary to the secondary on isolation transformer. And over here, I just demonstrate the EV1 mega charger, that is inductive charger, and then on the lower bottom center bottom is the plug, that where you plug the primary to the secondary of the inductive charger. People are also interested in fast charging. The reason is in the normal charging, it might take a few hours to charge the battery. And oftentimes, you may occasionally need a fast charge. So it will give you some energy so that you can drive a certain distance. In that case, you need a fast charger. A fast charge merely means that you charge the battery at a much higher current, so you can finish the charging in a shorter time. Charging the battery at a much higher rate will involve two issues. One issue is the battery life. You may damage the battery life if you charge at a too high rate. Secondly is heat. When you charge at a too high rate, the internal resistance of the battery will generate heat, and that heat needs to be managed. So in order to do a good fast charging and maintain the battery good life and deal with heat generated with the fast charging, you probably have to go with a post charge. What it means that you charge at a very high rate. At some point, you're going to stop for a while to have the battery settle down and to dissipate all the heat generated. And then once everything settled down, you start fast charge again. Or you can have a staggered charging, which means you can charge at a very fast rate when the battery SOC is really low. When SOC rises, you can slowly reduce the charge rate. Okay? So those three different charging diagrams are all used in fast charging. People prefer, different people in different design or prefer a different charging profile. Bidirectional charge is needed for a V2G application. A V2G means a vehicle is connected to the grid where you can transfer energy from grid to battery or from vehicle battery to the grid. In that case, you need a bidirectional charger. A bidirectional charger can be isolated or can be non-isolated. The non-isolated will have a much better charge efficiency, but it will have a potential problems because connection between battery pack and the grid, the direct connection. So it's not very safe in such a setup. Isolated bidirectional charge is a very complex system, and because isolation, the control is